My name is Ryan Foulon. So I have a bachelor's degree in psychology from the University of Colorado. I have a master's in experimental psychology from New Mexico State University, and I have a master's in statistics also from New Mexico State University. And I have a data science graduate certificate that I earned since I've been working here at TRAC. So that's a cool opportunity that TRAC affords its employees is to get graduate certificates. And they pay for it, of course, which is nice. And I've been working at TRAC for 3 years, a little more than 3 years. And I work for Sylvia in the Human Dimension Division. So unless there was something else, Steph, you wanted to say, I'll just jump into the briefing here.
Absolutely, take it away.
Okay, cool. Yeah, so Steph read the title is long and loaded, but the main thing that I'm going to be focusing on in this briefing is the MUMT. So that's the Manned-Unmanned Teaming, and that was the focal point of the study. And of course, we use combat models to kind of analyze the effectiveness of different levels of MUMT. And as far as the Armor Brigade Combat Team, that's just important to provide everybody a little context on the size of the unit, the composition of the unit, and kind of the operations that unit would be kind of conducting. So let's dive in. Okay, so this briefing, so the study took place a couple years ago. I think we finished it up in 2019, and I put together this briefing for a conference, a symposium, and that symposium was the Military Operations Research Symposium. Rick mentioned it. It's first of all, going to those things are really fun. It takes a lot of work to put brief together for it. TRAC puts you through the ringer. A lot of work goes into the briefing and practicing your presentation and everything, but it's really fun to go to these things and hear what everyone's working on across. So MORS is for all military services. So you get to hear what the Air Force is working on, what the Marines are working on, what the Navy's working on. So it's pretty fun. Okay, so but this briefing was kind of geared to that audience, right? So it's more geared toward the modeling, the specific model we used. So, but as I brief it to you guys, I want to kind of bring it up a level, talk more generally about the process and kind of the things that were more fun or different about the study. So that's kind of how I'll proceed from here. Okay, so essentially we examined how teams of manned vehicles and robotic autonomous ground systems could be configured to better perform in large-scale ground combat operations. And what the impact on operational effectiveness is when we vary the number of human operators to the number of robotic combat vehicles that each operator is controlling. So that concept is called span of control. So that was kind of the main factor that we kind of wanted to look at the effects of. When you vary that, what are the effects on operational effectiveness? So you might be wondering, okay, what's the big deal with operational effectiveness? Well, operational effectiveness is really the kind of like the bread and butter of TRAC. And basically what it means is that we assess the effectiveness of a capability or of a set of capabilities in the environment that they were designed to operate. And so as best as possible, we try to account for all the variables that capability or set of capabilities might encounter. So that includes the enemy, that includes the physical environment, the terrain, the weather, stuff like that. So, and we do that within models, big, complicated, some not so complicated, others more complicated, or I should maybe describe them as either higher or lower fidelity combat models. So at the bottom of the slide there, we obviously have to measure operational effectiveness. So those are some kind of traditional ways that we measure operational effectiveness, and the two that are in blue are the ones that became important as we analyze the results coming out of the model for this study. Okay, so how did we approach this analysis, right? So, well, first we get guidance from our customer, and so in this case our customer was the Army Sciences Board, and this study was the first one that I worked on when I started working at TRAC, and I think it was the second study that had been kind of requested by ASB, the Army Sciences Board, for TRAC to kind of conduct. And so we had a relationship with the customer, and of course, you know, as you work on studies and you work for the Army or different commands in the Army or even some joint military services, you build your customer base or whatever. And as you work with customers, maybe repeatedly, you build your reputation. So we had a bit of a reputation with ASB, and of course, every relationship is different. But okay, so I'll move on from that. But the guidance they gave us was what the human to robotic vehicle ratios were that they were most interested in examining. And so basically that's all they gave us. And so it was upon, you know, it was our responsibility to take that information and build on it, to build, to, you know, conduct our mission analysis, build our study design, identify all the methods, models, and tools that we wanted to leverage to ultimately answer the questions the ASB was interested in having answered for them. So given the human to robot ratios, we then began developing our MUM-T alternatives. And so the process that we generally follow is to kind of explore or construct what we call our measurement space. And what that really is kind of what are the key variables that you think are going to basically give you your measurement space to examine the effects when you vary those variables. So essentially, after conducting a lot of front-end research, you know, digging into the literature, talking to people who actually study autonomy and robots and operations for, you know, specifically for a living, we kind of settled on a measurement space that was mostly characterized by level of autonomy, enabling technologies, and also the human dimension, right? So how would roles, responsibilities be distributed amongst a manned-unmanned team, depending upon what the ratio of operator to robotic vehicle was. So once we developed our MUM-T alternatives, the next thing we had to do was basically figure out what measures, what data we needed to feed our models to explore this computationally. And so that required us engaging subject matter experts and also digging into the literature to see kind of like what people had done previously. What were the measures? What were the scales that people kind of used to measure these kinds of variables? So one other aspect that I'll point out before I move on is that we decided, and we thought it would be very important for our measurement space to account for basically how technology would increase the speed of or the reaction time of what we refer to as the kill chain. And so what the kill chain is basically the entire process from target acquisition to target engagement. And so another word for that is kind of the sensor to shooter process. So we thought that was going to be something that would help us elicit differences in the model. And so we really needed to kind of account for that and develop a way to measure that and instantiate it in the model. And so I'll get into that in a little bit in a couple slides. But for now, let's move on to try to give you a little better idea about manned-unmanned teaming, or at least the way that we conceptualized it. So generally speaking, so each new application of our models, for each new application, the model needs to be integrated with either the particular capabilities under study, and also with the data, and that supports, kind of the concepts that we're trying to get after measuring. And so there's a modelism, and it's, we call some of those, we call developing the model creating behaviors. And so that's kind of a modelism, because sometimes, you apply it to something that's inanimate, or not inanimate, but something that's not human, like a machine or a vehicle, and you say, oh, we're creating these new behaviors for this tank. But in our case, we actually were creating behaviors that you could call, that you would closely associate with human behaviors. And so 3 big behaviors that we created and instantiated in our models to help support the MUM-T concept were perception sharing, mobility control, and weapons control. So what we wanted to capture, really, with these 3 behaviors were the responsibilities of a 3-man Abrams tank crew. So a 3-man Abrams tank crew includes the commander, the driver, and the gunner. And so we wanted to basically account for all the behaviors of those 3 of that crew for the purpose of assessing the effects of distributing those responsibilities amongst a team that was comprised of human operators and robotic vehicles. So in this graphical representation of our MUM-T architecture, or our MUM-T systems of systems kind of architecture, you see a manned combat vehicle, and that's kind of represented by the box on the left. That's our MCV, and it's carrying all the human operators. 5 of those human operators are explicitly modeled, which means that they can be, basically killed or disabled. And 1 is implicitly modeled, and that's the kind of transparent guy there. And he just kind of basically enables the sharing of information amongst the different crew members. And so there's that idea of explicit versus implicitly modeling that I'm not going to get into, but I'll just touch on there. Okay, so also in that MUM-T systems of systems diagram, you can see on the right the 2 robotic combat vehicles. And so inside the RCVs are robotic counterparts to the human operators that share more or less of the responsibility for driving, gunning, and decision-making, depending upon the level of autonomy and enabling technologies. And that's really determined by the MUM-T ratio. And so this graphic is representative of a 2-to-1 human operator to robotic combat vehicle ratio. And this is the greatest number of operators per robotic combat vehicle that we explored. So this had the lowest level of autonomy and the lowest level of artificial intelligence, if you will. Basically, the gunner operator and the driver operator were just remotely controlling tanks, essentially, and there wasn't much autonomy instantiated for this alternative. So that leads me to basically to our study design. And so generally, a study design helps us break down the problem when it comes time to analyze the model output and draw conclusions from the analysis results. The design helps us trace the results back to the input variables to hopefully draw some conclusions about what's causing what we're seeing, what the effects that we're seeing coming out of the model. And so our study design consisted of a base case and 3 MUM-T alternatives. And so the base case is essentially just that 3-man Abrams tank crew. And each of the alternatives are pretty much defined by the MUM-T ratio, the ratio of human operators to robotic combat vehicles. And then as far as, if you go down the table row by row, those are all the variables that we saw as being as accounting for the different levels of autonomy and as well as the different enabling technology or artificial intelligence. And so, so basically, as you can see, the force size and more impactfully, firepower increased as the number of RCVs to human operators increased. So that was going to have a big effect. As artificial intelligence got better, robotic combat vehicles could operate at greater distances from their manned combat vehicles, as well as at greater distances from other RCVs within the MUM-T. RCVs could move faster, and they could carry out the kill chain process faster. Or, more appropriately stated, enable a faster kill chain. Because legally speaking, humans must always make the final decision when it comes to firing a weapon. So we're not going full autonomous here. We're not yet at, we haven't yet achieved Skynet, yeah, there's always a human in the loop when it comes to firing a weapon at something. So, so before I move on, and as I mentioned earlier, I want to touch on this kill chain reaction time variable that's down there at the bottom. So, so Sylvia in her talk mentioned that oftentimes there isn't the information that we might need to support something that we think is important to instantiate in a model, and so it's incumbent upon us and our creativity and also experience in the field, and also our background with be it psychology or design or psychological measures, to create a way to estimate the data that we need. And so in this case, we had to do that for creating this coefficient that would basically modify the kill chain reaction time depending upon the MUM-T alternative. And so essentially what we did is we had a lot of information about the base case. We had a lot of information about the kill chain process and associated times for carrying out that process for a 3-man Abrams tank crew. And so we built that, we built that process map in very great detail. And then we kind of systematically analyzed it and found where in that process the integration of autonomous artificial intelligence would basically either speed it up or slow it down, as was the case with alternative 1, when a human is needing to operate a remote vehicle, or possibly more than one remote vehicle. But there's a play there, right, between how autonomous is that system, and so that's how we developed those coefficients that either sped up or slowed down the kill chain reaction time, and that was fun. I kind of led that effort, and I had a good time doing it, and it kind of points out it shows that there is room for creativity in our job, and so I'll just move on. Okay, so now I'd like to describe the model more dynamically. So OneSAF, which is the model that we use, has a very useful, somewhat canned behavior, and I think it's actually called move. And so I'll explain to you how we further developed the move behavior for MUM-T, and some of the challenges we encountered in representing MUM-T movement at the necessary level of fidelity to get the effects we were looking for over our MUM-T, across our MUM-T alternatives. So in the model, after the movement issue was ordered, the unit, which in this case was the MUM-T, would follow a prescribed route. Now, the link between the MCV and RCVs was explicitly modeled, and why is that important is that it could be disrupted due to any number of causes. So, for example, the RCV could outrange the MCV, and the link would be lost, or some kinetic effect imposed by the enemy could either disrupt or disable the link. So basically, the link needed to constantly be monitored, as did the tactical spacing amongst the entities in the MUM-T. And so that was kind of done by the mobility control agent, as well as some maneuver algorithms that we developed in the model. So also, depending upon the alternative, more or less autonomy retained by the RCV would impact its ability to be resilient to lost link. And so algorithms needed to be developed basically to account for the different loss link contingencies that would occur for the different MUM-T alternatives, depending upon the level of artificial intelligence and such. And so some of the challenges we encountered were that the terrain, because we are actually operating on terrain that's representative of a place in the world, all the hills, mountains, and trees that would be there. So the terrain placed natural constraints on some of our variables, like the increased speed and spacing that was associated with the alternatives that had more artificial intelligence and technology. And because we were analyzing a problem that hadn't really been thought about in much detail, at least not at an operational level, there really wasn't a lot of information or data out there for us to leverage. Like, for example, when we had to develop what the loss link contingencies would be, we pretty much had to do that on our own and then validate that with subject matter experts. And so, again, that's something that we encounter with studies like this, is that we encounter problems that had really never been thought about or worked through. And so it's incumbent on us to use our problem-solving skills and teamwork to come up with some viable solutions that we then validate with subject matter experts. And so that's pretty fun. It can be fun, it can be stressful, but I think it's a fun part of our jobs. So now I'll move on to describe to you kind of the counterpart to move, and that's shoot. So like move, shoot is another basic behavior in OneSAF that we had to adapt for this study. And so one important attribute of MUM-T that we want to account for was that after any entity in the MUM-T detected a target, that information was shared across the MUM-T via the perception sharing behavior that we developed. And then the appropriate shooter was selected automatically using algorithms that we developed. So the obvious benefit there is that on top of the MUM-T increasing firepower and capacity without putting additional humans in harm's way, MUM-T makes the kill chain process more efficient and resourceful. And so, those of course are keywords that Army senior leaders, salivate over. So we wanted to make sure that if that was in fact true, we accounted for it in our models. And so from a programming standpoint, a number of challenges, we encountered a number of challenges with developing the logic that enabled the perception sharing and target prioritization. And again, there was not much information available for us to base some of our kill chain analysis upon. But again, that's what we do really well here. We get together as teams with different backgrounds and skill sets, and we work through these problems, and it can be a lot of fun. So that's how we solve that problem. Okay, great. So ultimately, we were able to provide insights into the operational effectiveness of MUM-T. So in particular, we found that not only does the addition of MUM-T result in increased lethality, and that's an operational effectiveness measure metric, I should say, that we measured by the number of kills of enemy systems, but it does so at the expense of fewer friendly personnel losses. And so those are pretty good operational effectiveness insights. Some of the factors that contributed to the results, and that's, as I mentioned before, we're trying to go back to our study design to determine what really drove these results. So some of the factors were the greater RCV to MCV standoff that was enabled by the increased artificial intelligence and technology in the later MUM-T alternatives, as well as the increased firepower that came along with the greater human operator span of control of RCVs. And especially, as you can see, those high bars on those two bar graphs, or the high bar on the left and the low bar on the right for the alternative 3, especially in alternative 3, when you had a ratio of 1 human operator for every 2 robotic combat vehicles, they did pretty well without experiencing many losses. So, okay. So, as I mentioned to begin this briefing, this was really kind of made for a different audience. It was made to, and these conclusions kind of speak more to the model and the modeling achievements and stuff like that. But I do want to focus on the last bullet point there. And what that basically says is that there are limitations to this analysis and these results, and that's going to be true of every analysis and every model. And here we just point out a few, but here we point out that further investigations probably need to focus more on the human cognitive workload, and what the training requirements might be as humans and robots become more and more integrated to actually realize the operational effectiveness benefits that we kind of alluded to with this study. So, okay, took a little longer than I thought it would take, but I think there's time for a few questions if there are any out there.
Ryan, it's staff. That was a great presentation. I really liked and enjoyed how you tied back this study to how enjoyable it is to working at TRAC, and giving the personal experience on how you use your skill set.
Yes, thanks, Ryan. Also, it looks like Alberto has a question. Go ahead, Alberto.
Really good presentation. Probably my question is, I know that you guys go through a lot of new problems that haven't been approached in any sort of previous context. About how long per project do you guys spend working on it? Is it anywhere between like a couple of months, maybe a year or so, or maybe longer? Because I know these are very new problems that you guys face at a consistent rate.
That's a great question. So, so the short answer is that it varies, and it varies widely. And so for instance, this project took us about 9 months. And as I mentioned, it was the first project I worked on when I came to TRAC, and I think that was pretty typical. It wasn't like so historically TRAC has done kind of more formal analyses that are called AOAs, alternative analysis of alternatives. And so because of so those specific kinds of analysis come with a lot of requirements, which basically just expands the time of the study to, I don't know, somebody else can maybe answer this better than I, but like years, like on the order of 1.5 years to 2 years. So this one wasn't officially an AOA, so the time frame that we had to conduct it in was condensed because it didn't have all the requirements that come along with kind of the formal requirements that come along with an AOA. But since then, since I did this project, I don't think I've worked on, maybe the second project I worked on had about a similar timeline, but it seems like since we have kind of TRAC has become more important, if you will, within the command that we fall. And I don't know if this is a good or bad thing. I mean, it's good that we're more important, but it seems like we're asked to do things faster and faster. And I think that's just the nature of it. Here, Rick has just popped on. He's itching to say something, so I'll turn it over to Rick.
Hey Ryan, thanks. That was a great brief. And Alberto, so your question, key point is we scope the analysis to fit the required timeline. So whenever we start a study, we're going to talk with the person that's asking for it, and it varies from somebody that's kind of a peer organization or that needs some analysis to support their work, or sometimes the senior people in the Army. But we're still going to sit down with them. We're going to work through, well, what do you need to know, and when do you need to know it, and then we figure out the best way we can answer it. And we always cover that discussion with a set of constraints, limitations, and assumptions. So we write down constraints. You got to have it by this date. We understand that. Limitations. What part of what you want can't we address? We just, we know you want it. We can't get to it, but we agree for that up front. And then, usually to go along with those as limitations, we're going to make an assumption that there's no data that exists for how long it, how fast the computers can, or Actually, I think for this study, it was, can one person really control 3 robotics vehicles at the same time, or something of that nature? We don't have any data, so we're going to make some assumptions, and we're going to come up with a number that is agreed to and good enough for this analysis. And when we work through the study, keep those CLAs. Of course, we got to make an acronym. Keep those in the forefront. Make sure everybody understands that as we go through, and then we deliver product, on time. I mean, a lot of times, studies end up getting broken into multiple parts because of that. We'll do a follow-on study and try to get to those other questions that we couldn't answer initially. But I'd say the easy answer is right now we're running probably 6 to 9 months. 6 months I'd say 6 months to a year is kind of typical. But as Ryan mentioned, with the Army Futures Command, which basically was stood up to enable faster analysis and ensure analysis to support enable acquisition, I should say, and analysis is part of that acquisition process. Their whole mantra is we're going to go forward, we're going to make decisions, and we're going to make decisions with the best available information. So we've been asked to do a lot of quick turn analysis, a month or two, find out what you can about this topic and get that, briefed up to senior leaders immediately. So, nature of our work's kind of shifting, but the key part is make a contract with the sponsor up front and then execute to what we've agreed to.
Okay. Yeah, thank you. Thank you very much.
So I heard, you want to jump in here, Steph, but I'll just tell anybody on the call, you can email me. I don't know if we're giving out emails, Steph, or whatever, but if you have questions, follow-up questions about this study or work at TRAC or anything, just shoot me an email. I'm an alumni of NMSU, and I really I want to support the community in any way I can. So just hit me up and ask me whatever questions you might have. Over.
Yeah, they've got the email address that's a group email box. They can send questions there and we'll connect people up with you. Ryan, thank you so much. We're going to take about a 13-minute break before we go on to our 9:15 presentation with Mr. Dickerson. Thanks again, Ryan.
Okay, thanks everybody.